Imagine a massive e-commerce platform, right? And it's right during the peak of a holiday rush.
Oh, the worst possible time for things to go wrong?
Exactly. The back-end service is just hammering away, processing thousands of transactions a second. And a developer pushes what they think is a minor update to the checkout microservice.
Let me guess. Written in a dynamically typed language.
You guessed it. So down in the logic, there's this function that expects to receive an array of user IDs from some external API.
Right.
But due to a tiny network hiccup, the API just returns a Boolean. It just returns false.
Oh, no.
Yeah. And the application accepts it. It doesn't flag any issues at all. Just hums along until it eventually tries to call like a dot map function on that Boolean value.
And the runtime just completely panics.
Complete panic. The microservice crashes, which causes this massive cascading failure, and it takes down the entire payment gateway for like 3 hours.
Wow.
I mean, millions of dollars just evaporate. All because a Boolean was masquerading as an array.
And the system had no idea until the exact moment of execution. That is, I mean, that's the quintessential runtime nightmare right there.
It really is.
It's basically the core argument for doing all the heavy lifting before the software ever leaves the developer's machine.
Exactly. And welcome to this deep dive. Today's mission is actually all about building the exact mechanism that prevents those catastrophic runtime failures.
Yeah, we're getting into the real security guard of the compiler today.
We are. We're pulling from your Lab 9 syllabus notes, Chapter 7 of Introduction to Compilers and Language Design, specifically from page 113 to the end, and also your professor's architecture slides.
Right. And just as a quick reminder, we did already cover the theoretical basis of Chapter 7 in our previous discussion.
Yeah, so today is strictly about the implementation side. We are zeroing in on how you actually build a static type checker for the B minor programming language.
Which is such a major pivot point in the compiler pipeline. I mean, if you look at your progress through Lab 8, you've already successfully built the scanner, to tokenize things.
Yeah.
And the parser to build out your abstract syntax tree, or AST.
Yeah, and in Lab 8, you actually decorated that AST too, right?
Yeah.
By resolving scopes and symbols?
Exactly. You connected the variable names to their actual declarations. So the structural foundation of the code is established and verified.
So what's left then?
Well, Lab 9 is where you enforce the logic. You're implementing the rules that guarantee the operations in the source code are mathematically and structurally sound. And you have to do this before you even consider generating any assembly code.
Okay, so the B9 type system basically provides the framework for those rules.
It does, yeah.
And the source material outlines some very specific constraints you have to manage in your code. So let's look at the atomic types first.
Sure.
You have your Booleans, your chars, void for empty function returns, and integers. And B minor is super strict here.
Oh, extremely. The specification strictly enforces 64-bit signed integers.
And why it's so specific?
Well, implementing that constraint ensures you have this uniform memory footprint across all your operations. It maps perfectly to the registers on a standard by 8664 target architecture.
Ah, okay, that makes a lot of sense. And I noticed the implications of those strict rules carry over to strings as well.
Yeah, definitely. B minor strings are ASCII and they are null terminated.
Right, so when you implement the type checking for a string literal, you're not just, validating an array of characters.
No, not at all. You actually have to account for the fact that the compiler must allocate an immutable block in the data section, and that has to include that hidden \0 byte at the end.
Right, the null terminator.
Exactly. So these static semantic rules dictate exactly how these fundamental types can interact, especially when we start talking about binary operators.
Yeah, the textbook lays down a really hard line on binary operators. So like addition, subtraction, multiplication, division, modulo, exponentiation, all of those require integer types on both the left and right sides of the expression.
Yep, and they absolutely must return an integer.
So if a user tries to, concatenate a string and an integer using a plus operator.
Your type checker has to intercept it right then and there and throw an error.
Okay, but what about comparison operators?
Now, that's where the implementation gets a little more nuanced. So operations like less than or greater than, those strictly require integers and they return a Boolean.
Sure, that tracks.
But the equality operators, equals, equals, and not equals, those are permitted for any atomic type.
Wait, really? Any atomic type?
Any atomic type, but they are explicitly forbidden for compound types, like arrays and functions.
Okay, I actually noticed that restriction in the architecture slides, and I was wondering about that. Like, why are arrays and functions blacklisted from simple equality checks?
Well, think about how C-like languages represent compound types under the hood.
Okay.
An array name or a function name decays into a memory pointer.
Oh, right. So it just points to a memory address.
Exactly. So if the language allowed a developer to use equals equals on two arrays, the generated assembly wouldn't actually compare the internal elements of those arrays.
It would just compare the memory addresses.
You got it. The programmer might be expecting this deep element-by-element value comparison, but the system would just execute a very shallow pointer comparison.
So you could have two identical arrays, same exact values, but if they're sitting at different memory locations, the program says false.
Yep, which is a massive source of logic bugs in C. So by designing B minor to throw a semantic error when equality operators are applied to arrays or functions, the language basically forces the programmer to write out an explicit loop to compare them.
That's actually really smart. You're implementing a guardrail that prevents a very common, very frustrating class of logic bugs.
Exactly. So now that we know the rules, let's talk about the engine of your type checker. How do we actually enforce this across an entire program?
Right. Because knowing the rules is one thing, but checking them is another.
Right. And the mechanism for this is a recursive post-order traversal of the abstract syntax tree. This is going to be implemented primarily in your expression type check function, or expiry type check.
Okay, so a post-order traversal. That essentially means evaluating all the children nodes before you evaluate the parent node, right?
Precisely.
I usually visualize this process like assembling complex IKEA furniture.
Oh, I like that analogy.
Yeah, right. Like you have the main dresser frame, which represents an interior node, say an addition operation.
Okay.
But you can't evaluate or stabilize that final frame until you've fully assembled and understood the smaller subcomponents, the drawers.
Which represent your leaf nodes.
Exactly. You have to evaluate the leaves, determine their properties, and pass those properties up to the parent node.
So applying that to your pipecheck.chec file, the implementation really does start at the leaves.
Okay, how so?
Well, for a literal expression, the type is self-evident. If your traversal hits an integer literal node, your function just allocates and returns a new integer type structure. It's very straightforward.
Okay, but what about variables? Because a variable node doesn't inherently contain its type in the AST, right?
That's right, and that's where the Lab 8 symbol table integration comes in. That's why you did that work last week.
Ah, okay. So your implementation has to follow the symbol pointer that you established in the previous lab.
Yep, you access the symbol table structure, extract the type information, and then you have to copy it using a type_copy helper function.
And then you just return that copy up the tree.
Exactly. So once the leaf nodes pass their types upward, the interior nodes can finally execute their logic.
Right. Back to the dresser frame.
Right. The expr type check function will recursively call itself on the left subtree, and then it calls itself on the right subtree. It takes the two resulting types and basically just runs them through a big switch statement based on the node's operator. So if the operator is addition, it verifies both return types are integers.
Wait, the textbook actually highlights a really significant memory management requirement at this exact stage of the traversal.
Well, memory leak issue, yes.
Yeah, because C requires manual memory management, right? And expr type check is basically a factory for these temporarily typed structures.
It's churning them out constantly.
Right. So let's say you evaluate the expression 5 plus 3.
Okay.
The traversal generates an integer type structure for the 5 and then another integer type structure for the 3.
Right. Those are your leaf nodes.
Then the distant node, the parent, verifies them and generates a brand new integer type structure representing the result.
And that's where the memory leak happens if you're not careful. If you strictly pass that new result up the tree, the type structures for the 5 and the 3 are now orphaned in the heap.
Because the pointers to them are just gone.
Exactly. They've been overwritten or they lost scope, but the memory was never freed.
And if you compile a program with, thousands of expressions?
Oh, this unchecked allocation will bloat your compiler's memory footprint incredibly fast. It's a huge problem.
So how do we fix it?
Your implementation must explicitly call a type_delete function on the left and right child types after verifying them, but before you return the parent's result type.
Okay, so you evaluate the data, extract what you need to validate the rule, and then immediately clean up the heap.
Exactly. You can't leave trash lying around.
Makes sense. Let's shift gears a bit and talk about what happens when things break. Like, how does the compiler handle violations?
You mean when the traversal discovers a semantic crime?
Yeah, like if some programmer attempts to divide a Boolean by a character.
Right. Well, obviously the compiler must fail. But the architecture slides really emphasize failing gracefully.
Failing gracefully. Okay, so how do we achieve that?
It really relies on a suite of helper functions. You'll need to implement type copy and type delete, like we just discussed.
Right. But the real workhorse of your semantic analysis is going to be type_equals. And listen, this function cannot simply be a shallow pointer comparison.
Oh, because B minor supports compound types. So type equals has to be deeply recursive, right?
Exactly. If the AST passes two array types into the function, you have to verify the overarching structure first, and then recursively check the subtype.
Because an array of integers obviously does not equal an array of Booleans.
Right. But actually, functions introduce the most complex equality checks by far.
Really? More than arrays?
Oh, yeah. Say you're comparing two function types, right?
Yeah.
Maybe you're verifying that a function prototype matches its later declaration.
Okay, that happens all the time.
So type equals first has to confirm the return subtypes match.
Right.
But then it has to traverse the linked list of parameters for both functions simultaneously.
Oh, wow. So it's walking two lists at once.
Yes. It must verify that parameter 1 in function A matches parameter 1 in function B, parameter 2 matches parameter 2, and so on. Wait, what if one parameter list is just shorter than the other? Like, what if they have a different number of arguments?
Great question. If one list ends before the other, the function must immediately flag an arity mismatch.
An arity mismatch. Okay, so when type equals eventually returns false during the AST traversal, indicating we have a semantic error, what happens next?
Well, the expert type check function has to log it. It increments a global error counter, and it prints an error message for the user.
Okay, that seems standard. But the text establishes this really counterintuitive golden rule for this scenario.
Ah, yes, the golden rule.
It says that even when an expression is fundamentally broken, expert type check must still return a valid type structure to the parent node.
I know, it seems totally contradictory. Why return a valid type for an invalid operation?
Yeah, should we just crash the compiler and yell at the user? I mean, the code is broken.
You could, but the alternative is halting compilation on the very first error you find.
And that's bad.
Think about it. If your compiler immediately panics and exits when it sees true +5, the programmer has to fix it, recompile, and then just wait for the compiler to crash on the very next error.
Oh, I see. So if they have 50 type mismatches scattered across a massive code base, they are forced to run the compiler 50 separate times.
Exactly. The developer experience would just be utterly abysmal. Nobody would want to use your language.
Yeah, that sounds like torture.
Right. So the industry standard is to report cascading errors in a single pass.
Okay, so by logging the error but faking a valid return type, your compiler allows the post-order traversal to just keep going.
Precisely. It continues evaluating the rest of the AST. So for example, if the code attempts an array index operation, like a bracket I, was actually declared as an integer.
Right, you can't index an integer.
Exactly, so you log the violation. But then your function might just return a copy of an integer type anyway.
So the parent node receives a valid type structure, which prevents a segmentation fault in your compiler itself.
Yep. And it suppresses those annoying false positive secondary errors further up the tree. You catch the real bugs without breaking the whole compilation process.
That is super clever. Now, speaking of logging those errors, the textbook offers an implementation strategy that I think will save people hours of debugging.
Oh, are we talking about formatting the error messages?
Yes, because standard C print statements become incredibly cumbersome when you're trying to output complex AST structures.
Oh, absolutely. Writing string formatters for every unique error message just creates this messy, unreadable source code. It's a nightmare to maintain.
Right, so the solution the book suggests is building a custom variadic function, typically named by print, using the standard arg.h library.
Variadic functions, those are how print accepts a variable number of arguments, right?
Exactly. In C, you use v_a_list to define an argument pointer, and then va start to initialize it based on your format string.
Okay, so how does that help us with the AST?
Well, you can iterate through the characters of your format string. And when the loop encounters a % symbol, it checks the next character.
Standard print behavior so far.
Right. But the textbook suggests inventing custom format specifiers just for your compiler.
Oh. So you could designate, say, %t to represent a type structure.
Exactly. When your myprint loop sees %t, it uses va_arg to pull the next argument from the list, cast it as a type pointer, and pass it directly to a custom type print helper function.
Oh, wow. The downstream effect of that implementation is incredibly powerful.
It really is.
Because when you hit a type mismatch in your switch statement, you don't have to write 50 lines of print logic. You can simply write my print, cannot assign %t to %t, right type, left type.
Boom. And the custom function intercepts those tokens, traverses the type structures, and outputs these beautiful human-readable strings like cannot assign Boolean to integer.
It transforms abstract heap memory back into the language of the programmer. That's fantastic.
It's so much better than standard C compiler errors. And implementing my print early in your workflow pays massive dividends when you're tracing issues in your tree traversal.
Definitely. Do not wait until the end to build that.
So true. All right, let's move into the actual logistics of the Lab 9 assignment, the playbook for this week.
Sure, let's break it down.
It involves pulling down the Lab 9 semantic analysis repository into your workspace, right?
Yeah, just a standard git pull. And when you do, you'll see your existing pipeline components, the Flex Scanner and bminerscanner.c, the Bison parser, the AST libraries.
And you'll also need to link the object files generated during Lab 8, right?
Yes, critically important. You need scope.o and symbol.o because your type checker depends entirely on the symbol tables they generated. If you don't link those, nothing works.
Okay, so what files are we primarily working in for this deliverable?
Your main focus resides in typecheck.c and typecheck.h.
And what does success look like? How do we know we're done?
Your success metrics are clearly defined by the provided test files. If you run your checker on good2.b, you should get a fully traversed AST and the exact output message, static semantics checks passed.
And if we run it on badsem1.b?
That should trigger your error handlers. It should output type check error alongside your properly formatted diagnostic messages.
Excellent. Now, looking at the syllabus, the professor strongly advises a very specific methodology for approaching an assignment of this magnitude.
Oh, yeah. Listen to the syllabus on this one. Attempting to write the entire expert type check function all at once, like mapping out every binary operator, every function call in one massive switch statement before running a single test, that is a recipe for absolute disaster.
It just overwhelms your working memory.
Completely. The cognitive load of tracking heap allocations across multiple recursive calls is way too high to debug all at once.
So building incrementally is basically the only way to manage the complexity of recursive tree operations.
Absolutely. The recommended approach is to implement the base cases first. Write the switch cases for integer and Boolean literals, compile it, and test it immediately.
Right, and then maybe implement the type copy helper function for variable resolution.
Exactly. Compile and test. Then build out the logic for a single binary operator, like addition. Isolate each component, verify the memory is freeing correctly, and really encode that knowledge before moving on to the compound types.
Because trusting the recursion requires absolute confidence in your base cases, right?
Yes. If your atomic type evaluations leak memory or return malformed structures, the interior nose will inevitably fail. And trying to trace the origin of that failure through a massive AST is just... it's an agonizing process.
Yeah, it sounds like a late night in the lab nobody wants.
Avoidable pain. Just build it step by step.
Honestly, this lab is such a turning point. It's the moment your compiler actually begins to comprehend the software it's analyzing.
It really is. Prior to this, the program was just a sophisticated text parser. It just knew where the brackets and semicolons were.
But now, you are implementing the mechanisms that guarantee memory safety. You're enforcing logical consistency.
You're protecting the end user from structural catastrophe.
Exactly. The constraints you are programming into bminer right now are the defining characteristics of statically typed languages. You are forcing the machine to resolve every ambiguity during the compile phase.
Which is such a stark contrast to dynamically typed ecosystems. It presents a really interesting architectural question, actually.
Oh, like with languages like JavaScript or Python?
Yeah. Those languages defer these exact resolutions until runtime. The interpreter has to evaluate the types in memory as the code executes sequentially.
And I mean, the flexibility of dynamic typing is often praised for speeding up initial development. You don't have to write out all these rigid type definitions.
Sure, it feels faster to write, but the trade-offs are deeply embedded in the execution profile.
Right. As you implement the hundreds of lines of C code required to verify types statically this week, you should really consider the operational cost of pushing that entire workload to the runtime environment.
It's massive. Every time a dynamically typed loop executes, the interpreter must burn CPU cycles, querying the type of the variables, checking their compatibility, handling potential exceptions.
It's doing your static compiler's job on the fly millions of times a second.
Exactly. And more importantly, consider the impact on system reliability. Think back to our e-commerce example. When a type mismatch, like a Boolean slipping into an array mapping function, lies completely dormant in a code base.
Until a specific user interaction triggers it in a live production environment.
Right. And everything crashes.
But by doing Lab 9, you are building the static defenses that make those runtime disasters impossible.
You're doing the hard work now, so the runtime doesn't have to.
Exactly. Good luck traversing the tree this week. Take it one node at a time, and we will catch you on the next deep dive.